Hi everyone, welcome back. I'm Shruti Mandaokar, and today's video has been on my mind for long. And today we're gonna be studying sorting algorithms because honestly, I'm excited about this one. And it's one of the topics that I wanted to revise since long. And I thought, okay, if I don't have someone to study along with, let me make a video by myself so I can reflect back and study more. And somebody needs to make this video. So, yeah. But honestly, until I started working on some ML algorithms and thinking about some product and how important sorting is, it all connected. And now I understood that, okay, I need to go back to my basics and see how it works. So I have my hot chocolate here, and um, I'm gonna study sorting algorithms. So let's understand why sorting algorithms is important and why sorting is everywhere. So before we get into algorithms, let's take 2 minutes aside and talk about why it matters. When we build data pipelines, one of the first thing that everybody thinks of is like how much sorting of the unstructured data is necessary. Right, the data in real world is messy, and to process and analyze it in dashboards and or do some data analysis, it's important that we sort them or order them in a particular manner. In Python, there's this simple function called sorted, and it works. Just we call sort and pass a list of something or an array or a dictionary, and it will sort it. But how does it work exactly, and why is it so fast even on huge data sets? Also, like if we keep this aside and think from machine learning perspective, think about recommendation systems. You use apps daily like Netflix, Spotify, and even Instagram. At some point in that pipeline, somebody is sorting. You have filters, you have sections and pages that you click to, and sorting also keeps your most liked preferences on the top. We sort our posts or sort items by a relevance score, and we also sort by recency, right? So the most recent post that you posted will often come up on the top. So we can directly think that Instagram or even Netflix pick and go for that sort that affects how your feed should appear. Okay, so this is example in machine learning. How about when we store data in databases? In MySQL, PostgreSQL, Cassandra, they are all built on sorted data structures. A database can find your data in milliseconds or out of a billion rows because data is sorted and indexed in a really clever way in the databases. That's why it is super fast. So this isn't just academic or a textbook thing. It's literally affecting your lives, every post, every second. And maybe you might not think about it actively, but as an engineer, as a software engineer, this is something that one should know. Take care of it. And once you see it, you cannot unsee it. Okay, let's start with basic algorithms, and I'm gonna pull up a Google Doc. So we're gonna write some notes together and revise this. It is a foundational structure in AI, ML, and databases, product, because a few examples would be recommendation scores in Spotify, other apps, recommendation engines, rank items by composite scores. They either sort by relevance, sort by recency, or more. Right, so many of the apps that you use daily use scoring algorithms. What else? Databases rely on sorted B trees, LSM trees for fast reads, Cassandra, PostgreSQL, distributed systems like Hadoop, Reduce, Apache Spark, implement distributed merge sort. Also, we have hardware systems like GPU inferences. Many more applications in daily life. We'll start with mobile sport. So in bubble sort, the idea is really simple. We walk through the array, compare two neighbors at a time, and if they are in the wrong order, we swap them. We keep doing this until nothing needs to be swapped. Everyone is in correct sorted position. Sorting can be descending or ascending from big to small, small to big. With each pass, the largest unsorted element bubbles up to where it belongs, just like how the biggest bubble in chai tea rises first in the top. Chai bubbles. Ah, chai bubbles. Also, okay. So this is the idea that we walk through the array, we compare two neighbors at a time, and if they are in the wrong order, we swap them. So concept is repeatedly compare adjacent elements and swap them if they are in the wrong order. Real world connection. Used in adaptive algorithm design. Refresh with new daily values chains. So let's see the code. Okay, so I'll share my screen. Hope it's visible though. So I'm sharing this online python.com, that is a Python ID which is online. So now we just uh, studied about sorting, and let's write the code for it. So I'm gonna write a definition. Will sort array, pass an array to it as parameter. I'll first calculate its length and then write a loop for I in range, and I'll declare a variable called swapped. So first swapped is false. Then for j in range 0 to n minus I minus 1. So leaving the first element from the last. If array j is greater than arrays j plus 1, if array 0 is greater than arrays 1, suppose, then we'll swap it. Both will interchange places. Then let's print vowel sort, and then we'll pass few elements. 64, 34, 5, 12, 2, 11, 90. Let's try running this so you can see it sorted. I was able to sort everything properly. So yeah, this is our code. I'm gonna paste it in our doc. Notice this swapped flag. That's like the smart part, because if we go through the whole pass and nothing moved, array is already sorted, we exited it. But here you can see um, there are like two conditions. So on would be for already sorted array, but this for loops also goes from uh, 0 to last second element, I guess. And then the
It's 4 o'clock.
Okay, so now we know bubble sort. Another example would be insert the image, got it from Google. So we have this number, this is unsorted. We'll compare first and two and we'll swap. Then we'll compare second and fourth and then we'll swap. And fourth and we'll swap. Compare fourth and fifth swap. We'll repeat it. We'll compare these two, swap. Compare these two and swap. Then these two and swap. Okay, time for another sort. We'll go with selection sort. So selection sort is has a different philosophy. Basically, instead of swapping all the time, we scan through sorted section, find the minimum element, place it in the front, then move to the next position, and then we repeat. Almost like one person, just me. This is how I do. Who looks the whole buffet first before putting a single thing on their plate. Very methodical. And it's like very selective. It does most in -1 swaps. Bubble sort can do many more swaps, but selection sort matters in embedded systems and IoT devices, places where writing memory is physically expensive. Like, for example, EEPROM memory that actually degrades with every write. So here in this case, like the fewer swaps we have, the longer the hardware life will be. This is a real use case of selection sort. Errors. Oh, was I not sharing my screen? I thought I was. Oops. Okay, so I don't know how much of it is visible, but I wrote the notes for sorting, why sorting matters, bubble sort, concept, the real world connection, Python code, the output, and how we compare one element to another. Then we started talking about selection sort, right? Instead of swapping all the time, we scan through the unsorted section. First, we find the minimum element, we place it in the front, then we move to the next position. It's almost like one person who looks at the whole buffet first before putting a single thing on a plate. And it does most in management times. It really matters in hardware systems where writing memory is physically expensive. The concept here is find the minimum element in the unsorted position and place it in the beginning. Repeat for each position. Minimizes swaps. Most n minus 1 swaps total. And the time complexity here is oh, first let's think about the code and then we can think about complexity. I'm gonna erase my earlier code and let's write selection sort. Okay, so I'll create a definition selection sort which takes an array as a parameter. Next I'll calculate the length of the array and create a row for I in range of n. Create a minimum index first. So minimum index, suppose it starts with 1. What is this? Really? 1. Yeah, now it's correct. Then for j in range of leaving the zeroth element from 1 to n, if array's particular element is less than array's minimum, bring minimum first. So we want the minimum at the first point and we'll swap it. Wait. We'll assign this to j first. Autocorrect off. Here we are doing at most n minus 1 swaps. So we're looking for minimum first. Let's run this. Is there some issue because it's not sorted? Oh, this is not 1, this is I. Starts with first 11, 12, 20. Now it's sorted. So yeah, I'm gonna copy this code and paste it. Time complexity is O n square. No early exit. Space complexity is O of 1 in place. Not stable though. This was about selection sort. Now I'm adding a picture to remember for my reference. So we can say we first look for the minimum element, then we swap it from index 0, and then we look for the minimum element, then we swap it, then we look for the minimum element and we swap it. And similarly, we swap everything until we find the smallest element, swap with index 4. So this was about selection sort. Now time for insertion sort. Insertion sort. Think of it as holding pack of playing cards. You pick a new card, slide it left until it finds its spot. That is insertion sort. We build our sorted array one card at a time. Concept is build the sorted array one element at a time. Pick each element and insert it into its correct position in the already sorted position. Playing cards, real world use. Online sorting, where data arrives one piece at a time. We need to keep it sorted as it comes in. Think of it like a live leaderboard. Players finish a race. Scores come in one by one. We need the board sorted after every update. Session sort is perfect for that. When the chunks are small or input n is small, insertion sorts. Simplicity beats fancier algorithm. Okay, so this is we can now code in Python. Mhm. Dun-dun-dun. 4:20 p.m. Okay, I'll change my tab to the coding ID now. Mm, yeah. Mm, okay, I'll remove this one. Okay, now I'm gonna create a function. Definition insertion sort takes in an array for I in range 1 starts from 1 till the end of the array. We'll have a key, variable key, which will hold array's ith element, and then j, which stores 1 before ith element. So we can say while j is greater than 0 and arrays j array of I minus 1 is less than array of I, or say key array of j plus 1 array of j to j minus 1. So here what we are doing, we are starting with the second element as first element is assumed to be sorted. Then compare the second element with the first if second is smaller and swap them. Then we move to the third element, compare it with the first two and put it in its correct position, and then we repeat until the entire array is sorted. So this is the approach for insertion sort. Start with the second element as the first element is assumed to be sorted. Pair with the second element with the first. If second is smaller, swap both of them. Then move to the third element, compare it with first two, put it in correct position, repeat until the entire array is sorted. So suppose online leaderboard simulation. So if we have a list called leaderboard, array def add scores leaderboard dot and score. Then we'll call insertion sort leaderboard for S in 95, 92, 78, 95, 88. So suppose this is our array. I'm gonna do add score and pass S to it. Then we'll print leaderboard. Let's see what output we get. So you can see it's sorted output now. So first it compared these two, put it in the sorted position, then it compared these three, shifted this here, and similarly everything happened. Gonna copy my code. So I'm gonna attach an image for myself to understand better of this. Insert image. Yeah. So we can see first it compares these two, puts the smallest in first. Compares these three, puts the smallest in first. And this four and smallest in first. Finally sorted. Yeah. Time complexity is n square first or average, and best or nearly sorted. Space complexity is O of 1 in place. Stable, yes. Next, let's move on to merge sort. Okay, merge sort. It is one of the elegant algorithms that yes to divide the array in half, sorting each half recursively, and merge the two sorted halves back together. You look at the front of each half. Please take the smaller element, build your result. Being stable in an algorithm means that equal elements keep their original order. So if you are sorting a product list price, and two items are both $5. The one which was higher in the original list stays higher. That is exactly what you want when you are doing multi-column sorts in data pipeline. But the real but Apache uses fundamentally merge sort in its workflow. So the map phase is dividing data across machines, splitting the array. The reduce phase merges sorted chunks like the merge step. So this is how hundreds of servers run instead of two halves of array. So when we are training an ML model, on a data set that does not fit in a RAM. We use merge sort to sort the data externally, reading and writing chunks from disk. This is called external sort and is used in large scale ML pipelines. Talk about Python code. The merge sort has two steps. One is like map phase and another is reduce phase. Okay, so I'm gonna create a function def merge sort takes an array. If length of array is less than equal to 1, we return array. We calculate the middle. So middle is length of array 2. We calculate the left and right half. So left half is merge sort slicing array of this to mid. Right is merge mid till end. Then we return merge left comma right, but we have to write this merge function now. So we're gonna write def merge left comma right result. I equal to j equal to 0, while I is less than length of left and j is less than length of right. Left of I is less than equal to right of j. Preserves stability result dot end left of I oh wait, chip indentation, yeah, else multi-column if we have products and key value, not key value, but like this. mm, A, comma 3, B, comma 1, C, comma 3, D, comma 2. Sorted products, merge, sort, and then we pass products. Okay. There is some error. Oh, I need to first print the result. See, A3, B1, CD. So both are 3, but A comes first because A is first in the order. The time complexity is here is O n log n. Always all for best, average, worst. Space complexity is O of n. Still, yes. Next we have is quick sort. It is a little bit chaotic sort algorithm. It is one of the fastest algorithms in practice. We pick a pivot element, we then rearrange the array so that everything smaller to the pivot is to the left and everything larger to the pivot is right. Now the pivot is in its final correct position. Cursively do the same for left and right sides. The magic is that after partitioning, we don't need to merge anything. Pivot is already done. This is why it is so fast, efficient, and quick. Uh, ranking so concept the concept basically is that we pick a pivot, partition the array, so all smaller elements are left to pivot, all larger elements right to pivot, and then we recursively sort all the sides. After partitioning, the pivot is in its final sorted position. No extra memory. So now let's try the Python code. Oh, actually, it is cache efficient and used for K recommendation systems. is my editor. So it is like one of the longest, but we'll try to write it down. So we're going to do import random, create a function definition quick sort, pass an array, pass low and high as parameter, but let's keep high to be none. Then if high is none, high make high the last element of the array. If low is smaller than high, and make a pivot index which calls another function called partition. Array low high and call quick sort. Partition the left half and the right half. And then this function is what we are writing, array low and high. And then we replace. First, let me write and mention here that quick sort is used for whereas quick select is used for finding the kth largest element. Okay. Definition quick sort. If no high provided, set it to last index. Continue only if partition has more than one element. Here we are saying partition the array and get pivot position. Recursively sort left side of the pivot. When we recursively then we have the partition function. Choose a random pivot for safety. Random index, random, low and high. Mm, s- Swap the particular random pivot with the last element. So I'm gonna do array random element, and then my last element is array of high. I'm gonna swap both of those. Array of high swapped with array of random index. Okay. Find the pivot element. Pivot array of high. I equal to low minus 1.
It's 5 o'clock.
For j in range low comma high, then we swap the smaller element to the left side. So what we are doing, we are finding the pivot element. We keep track of smaller traversing element from low to high minus 1. Current element is less than the middle or pivot element. We move boundary of smaller element, and we swap smaller element from right side to the left side. Place pivot in correct sorted position to array of I plus 1, array of high, array of high, array of I plus 1. Then we turn pivot index. Now we have to write another function called quick select as well. So for that, we know quick select finds kth largest element efficiently, right? We wrote here. So finding the largest kth element. So let's write its function. Quick select. So I'm gonna wait for what quick select. I'm gonna try definition. I'm gonna do quick select array and k. First make a copy of array. So I'm gonna do array equal to array dot copy. And I'll make a recursive helper function, which is gonna be def helper. No, actually def helper nahi, def select low and then high. I'm gonna write the base case. So base case is when only one element is left. Low equal to high, then return array of low. Otherwise partition array. Use pivot index equal to partition array low high. And to find top kth element, first we are making a copy. When we are saying when we have just only one element, then we return that. Otherwise, if we have more element and we want to find top 2 or top 3, then we partition the array. And we rank from right side. For example, my largest is rank 1. Second largest is rank 2. So I can say rank equal to high minus pivot underscore index plus 1. Because partition and then plus 1, I think I might have to revise this one again. It's a little long, right? We should read like W3 School's article or somewhere on that. If we found the correct kth largest, then we return that. Otherwise, we return search the right side elif k is less than rank. Return select pivot underscore index plus 1 comma high. 0 comma length of array minus 1. I'm gonna print a random array now and see if this works. So let's print scores. See if it's able to return in 0.3, 0.7, 0.5, 0.95, 0.1, print original array. So original array would be print scores, and then we'll do quick sort. Sorted underscore scores equal to quick sort scores dot copy. Make a copy, print So we'll print the kth largest element will be quick select call scores. What do we pass? Array and k, right? So scores index and then our k. Here I think I made some small mistake. It's IDX. That is why it was showing red. And then I don't want it to be indented. Okay, need to be outside. Let's see. Okay, seems right. Forgot. What I did was inside quick select I made partition. So now I placed it outside, so should be okay. And then this goes here. Okay, all good it seems. Run. Problems. Trailing white space. Line 8 column 21. Looks like this is working. We can see this is the original array, this is the sorted array. Second largest element is this one. This is literally used in recommendation systems. Wow. Should make a project out of it. Okay. I'm gonna copy this code to my doc. So this was quick sort. We had three functions. Which ones? One was quick sort, partition function, then quick select. Oh, very well, very well. Okay. So, what were the pivot strategies? First is last element. Simple, but O n square. It's the time complexity on sorted arrays. Another could be random pivot, right? So this will be expected O and log n, but is safe for production. And there can be median of 3. Best practical performance. When it comes to time and space complexities, time complexity is O of n log n average and O square worst with mode pivot. Space complexity I think is O log of n with call stack, not that stable. So this was quick sort. Now it's time for heap sort. I'm gonna take it to the next page. Yeah, better. So, is there any image that I can refer for quick sort? Let's see. Images. I'm gonna keep this one for reference, for my reference to fix it better. Oh, what happened? What did I do? Mm. Yeah, okay. It's odd. Alright, time for heap sort. Okay, let's read what heap sort is. When it comes to heap sort, as far as I remember, it consists of a concept called max heap. A max heap is a tree where every parent is larger than its children. The root is always the biggest element. Heap sort works by, first, what we do is we build max array seed from your array. So we'll first have array. We'll make sure to build max heap where every parent is larger than its children. The reason heap sort is valuable is not just the sort itself, but it is the heap data structure underneath. Heap powers priority queue, which show up everywhere. So, we have Dijkstra's algorithm used in Google Maps to find shortest paths. And then we have Kubernetes job scheduler, which pod should run next. Then we have Apache task queue. Okay, for in machine learning. When we ask, find the top 10 items by popularity, it is a heap operation basically. Python has something called heap queue function, which helps does this in O of n log n way faster than sorting the whole thing. Let's write the code. Okay, so this was quicksort code. I'm gonna refresh it, delete it. Now let's write quicksort heap sort code. Def heap sort takes an array, calculate the length of the array, for I in range of sorry, not quicksort, it's heap sort. Sorting algorithm using a max heap. So we have a function. We first get the length of the array, then step 1, build a max heap. Start from the last non-leaf node and heapify node. So a few nodes. Heapify is basically function that converts part of array to heap. sort parent node is always greater than children. Largest element stays at the root. So basically, what does EP5 do? EP5 checks is the current parent smaller than the children? Yes or no? So that's why it's helping to build the heap. Okay, so for I in range, okay, before writing the code, I think we should understand it through an example so that it becomes easy. I'm gonna go back to my Google Doc. Okay, let's see. So imagine if my array has elements 4, 10, 3, 5, and 1, right? And my n is 5. So step 1 will be convert array into a tree. So tree will have index and value. So my element is 4, 10, 3, 5, 1, right? Index is 0. So index is 1, 2, 3, and 4. Okay, and now tree representation could be like 4 sits at top, index 0, right? And then where is that line? Okay, here and here. Ten sits at index 1, 3 sits at index 2, I should do this, or wait, it's understandable, right? Then 5 sits at index 3 and 1 sits at index 4. So this is my tree now, right? So Step 2 is find last non-leaf node. So this is root and these are like nodes, leaves. So here this one does not have any leaf, right? But even we have a formula for that. It's mod of n division by 2 minus 1. So when we solve this, we'll get our n is 5 mod 2, 5 division by 2 minus 1. Remainder is 2 minus 1, which is 1. So when I write 4, so a for loop could be like for I in range 1 comma minus 1 comma minus 1. When I write something like this means we I equal to 0 and we heapify nodes I equal to 1 and I equal index equal to 1 and index equal to 0 and not 2, 3. Because 2, 3, 4 already automatically satisfy the heap property, right? Because see, only in these two cases the parent is not greater than the root, but here it's already satisfied because they have no children. We fix only parent nodes. So let's first iteration. So in our first iteration I equal to 1. So we will run this command. When this happens, the tree becomes like this. Yep, like this. So this is the original first iteration. So what is the node at index 1? It is 10, right? What are its children? Left. On the left of this is 5. Index 3 equal to 5. On the right we have index 4, which is 1. Then we check, is 10 greater than 5? n is greater than 1. Already valid max heap here. No changes. Array remains same. Now we will do second iteration. I equal to 0. Then we'll have heapify 0. And similarly this as well. But here node at index 0 is 4, right? Children on the left is 10, on the right is 3. Largest is 3, 10. So we and then we do this operation. So now my array becomes so tree becomes this 10, 4, 3, 5, 1. But as you can see here, this is broken as 5 is parent, 5 should be here and 4 should be here as 5 is greater. So subtree at index 1 is broken. So heapify runs recursively on index 1. Now there is something called recursive heapify. Which is like at index 1. Children are 5 and 1. Among them, largest is 5. So we swap again. And it becomes this. Final array, final tree. As you can see now, everybody is sorted. The root is the largest, and in everything, the children are the smallest. It is a max heap now. So this is the logic basically. Okay, well, now we can shift to the code successfully. So we use the function called heapify array comma I. Then for the next step, we can do extract and one by one, move current root just element to the end. So for I n minus 1 comma 0 comma minus 1. Not a 1, it's I. Made it better. We'll write the function heap if it's undeclared, right? That's why it's showing this error. Function heapify. So let's write. Let me give some space. I'm gonna do definition heapify. Takes an array. Takes a number and assume the current node is largest. We'll assume this. So largest equal to I. Then we'll find the left child index. Left is 2 multiplied by I plus 1. By the way, this is index. Right child index. So we write equal to 2 multiplied by I plus 2. Check if left child exists and is greater than root. If left, then n, and if left child exists and if left child is greater than root. Root is always the largest, so this is the array of largest. Sorry, this should be left. Then check if same thing, but now for right. If largest is not the root node, swap root with largest child. Left child index, then right child index. We then check if root, which one's greater than root. We want to make sure that in any heapify function, the root is always at the first. So we swap the root with the largest child and then we recursively call this until it's fixed. What is this? Okay, some just minor error it seems. So what are we doing here? We are doing 5 steps basically. We are building max heap and we are swapping largest to n, reducing heap size. We are heapify again. We repeat until sorted. Okay, now let's test it. Test the code array. So if my array is 4, 10, 3, 5, 1, I'm going to print sort, sorry, not sort, heap, sort, pass array to it. Let's see what happens. As you can see, it's sorted. So this our code is working fine. I'll copy it and paste it in my Google Doc. Wait, was I not sharing it? I was able to write this whole code. I guess I forgot to share the screen, but this is the code. And you can see it's properly sorting it as well. And there are comments for anyone to refer. And copy this and I think these are important for now. Rest, there are three more sorts which I'll revise later, I think. One is radic sort, counting sort, and then Tim sort, bucket sort. So I'll do those later. But for quick sort, not quick sort, for heap sort, I think we are done with heap sort. You can see the complexities of and low in. I'm checking if I can find any image for my reference. Okay, great, amazing, major sorting algorithms revised. Okay, I'll revise it again tomorrow and tonight before sleeping too. But basically, there is this cheat sheet that I have, which I'm gonna attach for my reference. It's like for referring and comparing. Yeah, this one. So you can see bubble sort best is off and average O n square. Teaching only fastest and practice quick sort. Oh, also, I have one another real life word usage. So I'm gonna write that too. Insert image. Not this. Yeah, look at this one. Bubble sort. Wait, am I sharing the screen? Yeah, I am. Bubble sort never in production. Selection sort IoT embedded as well. QSOT, Google Maps, NLP pipelines, GPU deep learning, Redux sort buckets. So I still need to revise these four, but I covered these 1, 2, 3, 4, 5, 6 sorting algorithms with code. Example. I'll follow this. Okay, cool. Thank you guys for joining me.
It's 6 o'clock.
Thank you for joining me. I'll see you guys again. Thank you for joining me. It's almost over.